This time, without a doubt, we have the most complex, expensive, grueling and time-consuming project in the history of the channel. Thousands of holes, hundreds of meters of fiber optic cable, 100 sensor detectors. All of this stretched out over half a year and made half the team's eyes twitch. But in the end, it was worth it. Enjoy the video. This story began 6 months ago, and to get ahead of myself, I'll say this is the most difficult, nerve-wracking and lengthy project in the workshop's history. But despite all the challenges, it was worth it. The first thing we did was choose the material. Here we decided to show off a bit and make the tabletop from a single slab of ash. First of all, we leveled the tabletop using a router. This is done with a router bit like this one, with replaceable blades. And let me tell you, that's a very handy feature. You really appreciate it after the bit hits a nail or a piece of shrapnel. Yes, we've had that happen before too. As a result, you only have to replace a couple of blades, which are quite inexpensive unlike the cost of the router bit itself. As always, you'll find links to all the tools, accessories and materials in the video description. Meanwhile, pass by pass, the CNC shaved off a couple of millimeters at a time, and in the end, we have a perfectly flat slab, in other words, a wide, live edge board we now need to turn into a straight edge board with even sides. To do this, we mark the center, take a sliding miter saw and trim the workpiece in several passes. One of the sides was cut off in the same way, and now, using one straight edge as a reference, we cut the other, opposite side. But this time on the table saw. Yes, it hurts me too to see such a beautiful natural edge go to waste, but that's what the table design requires. Next, a formwork was made and all the cracks were addressed. We lightly pour fast curing resin called Art Eco from Ekovani into them. We tinted it slightly with a dark dye. This is the primer layer. After it's set, we mixed up the ART massive compound for large pores. We tinted it with black dye and poured it in generously, as if from a bucket, to make sure the entire tabletop is solidly cast. A week later, the resin had cured and we could dismantle the formwork, which is what we're doing now. The next step is calibration again. We take the now familiar router bit and remove a couple of millimeters in a single pass. This is done so we don't have to sand the epoxy for several hours. So, according to the plan, the tabletop is supposed to imitate a starry sky. Here we based it on a real map with all the constellations. And this is what that map looks like. The constellations are straightforward. They have a precise arrangement. But when it comes to the number of stars that will serve as the background, that raised the question. That's exactly why we're making a sample on paper. The thing is, when you look at the image on a monitor, it's hard to tell whether 1,000 holes will be enough to make it look impressive. That's why we are making an exact copy of the starry sky on paper. We look at it and realize that 1,000 holes is nowhere near enough for a tabletop like this. Then we try 1,500 holes. We gather the team again and come to the conclusion that we need at least 2,000 small background holes, in addition to the main constellations. So we've settled on the number of stars. Now all that's left is to prepare the surface onto which we'll transfer the starry sky. To do this, we flip the blank over and carve out a recess. In the end, we need to get a tabletop made from a solid slab that looks massive, but all the inner workings will be hidden inside. That's exactly why we leave a border on all 4 sides. Also, the electronic components, specifically the touch sensors, have their limitations. That is, if you attach them to a 5 cm thick surface, they won't work since they can't penetrate that thickness. But if you remove the main bulk and leave just a 1 cm thickness, they work perfectly, and the border we leave will give the appearance of a massive solid tabletop, just like it was originally. But not everything went smoothly. Such a construction made from a solid piece of wood isn't particularly stable. We understood this, but still decided to give it a try. As a result, after hollowing it out, the tabletop warped quite a bit, so we decided to press it against a flat surface and fix everything in place with epoxy. The next day, the resin had cured and we started cutting out the holes for the sensors. Overall, the resin did its job and the tabletop more or less leveled out and seemed to hold its shape. But it's important to understand that the resin filled the volume and the thickness became greater than what we needed again. And this is very important for the proper functioning of the sensors. And here we made a fatal mistake. One of the edges of the tabletop was poorly secured and the edge bent upwards. As a result, several grooves for the sensors were cut all the way through, irreversibly ruining the tabletop. In the end, after 2 weeks of working with this tabletop, we abandoned the idea of making it from a solid slab, since it still kept twisting, warping and deforming. And after the final calibration, this is what it looked like. In the end, we decided to make a simple, reliable and straightforward panel, glued together from oak slats. That's what we're preparing now. First, we cut the boards into smaller pieces, discarding the hardwood along the way, since that's the most unstable part. All defective pieces with knots and cracks also go into the trash. The next step is to use a miter saw to cut the boards to the required size, again discarding any defective sections. Once we have perfect blanks, all that's left is to level the surface. The first step is to run them through the jointer, pass after pass, until we get a perfectly flat surface. This is done quickly and effortlessly thanks to the helical cutter head. This is what it looks like. Then, using a planer, we level the opposite side. The planer also allows us to make all the boards the same thickness. And after 20 minutes of work, we have this beauty which just needs to be glued together. It's all simple here. Good glue and convenient clamps. Additionally, besides the main clamps, we secure the panel with bars on both sides to ensure that all the pieces stay in the same plane. Evenly squeezed out glue indicates that it was applied properly and in the right amount, which is a sign of a good glue up. After a couple of hours, the glue has dried and the panel can be trimmed to size. To do this, we install a suitable blade and, using a sliding miter saw, give the tabletop the correct shape and the required size. You remember regarding the number of stars, we've already decided that, in the end, there will be not 2000 but 2500 of them. That's what the CNC is working on now. Most of the holes are made with a drill, 0.8 mm. And to be honest, I'm thrilled with how the machine handles this. By the way, I used to do these operations by hand and the drill bit consumption was at best 2 to 3 bits per 100 holes. And here's why. But the CNC does this almost without any losses. Of course, that's if the drill bits are of proper quality and well sharpened. Meanwhile, the machine has made over 2000 holes, so now we can switch this thin drill bit to a 2 mm one, since we decided to highlight the main constellations with exactly this difference. In other words, the constellations will be 2.5 times larger than the main background stars. A bit later you'll understand everything and see it clearly. As a result, the CNC drilled several hundred more 2 mm holes, which precisely replicate the main constellations. The next step is to flip the tabletop over, secure it and do the routing again. Attempt number 2. But this time we're dealing with a properly glued panel, which shouldn't bring any surprises. And overall, that's exactly how it turned out. As you can see, the panel with the rooted section is flat and stable, which means we can now mill the recesses for the sensors. You can see this on the screen. To move forward, we need to paint the tabletop, but first we cut off all the excess. The panel was originally made with some extra material to make it easier to mount on the CNC, but now it's time to remove the traces of that convenience. We cut off the excess lengthwise using a stationary machine, and it's more convenient to trim the ends with a sliding miter saw. That's exactly what we're doing. As a result, we have a panel with precise dimensions and a border around the perimeter. Now it can be safely painted. The first layer applied is wood stain. Of course, I could have left the natural light color of the wood, but in my vision it should be a dark color, so that the stars will shine brightly in contrast. The second layer is varnish. In our case, it's a matte varnish. The backside is also coated with varnish, since wood is a living material. It breathes and is very sensitive to changes in the environment. That's precisely why it's always best to treat it equally on all sides, in every dimension, to significantly minimize the potential risk of any deformation. The next stage is the most interesting one: creating the starry sky. For this I ordered 2 spools of fiber optic cable. So we have 2 spools of fiber optic cable and a tabletop with 2500 holes. All that's left is to put this puzzle together. First we number all the spots for the future sensors. In total there will be 120 of them. But we start with the first 30 players. To organize all of this, and then somehow connect it all, we made this kind of panel and started threading the fiber optic cable through these holes, and then they go to the corresponding sensor area. That is, through hole number 1, we run about 20 to 30 fiber optic rods and attach them around the pad with the same number. In the end, the fiber optic cable didn't fit through all the holes, so we had to slightly enlarge them with a drill. We spent an entire day just to realize that this method was really inconvenient. So we decided it would be easier to first run all the fiber optic cables and only then form them into bundles. That's what we spent the next week doing in shifts, since such monotonous work can drive you crazy. But this approach really did turn out to be more convenient. First of all, we started threading the fiber optics from the front side of the tabletop, and on this side the holes are much easier to see, because it's dark. Secondly, at this stage, there's no need to form them into bundles, which also makes the work easier. And so, hour after hour, day after day, we kept going, cutting hundreds of half-meter fiber optic strands along the way. Meanwhile, work in other areas wasn't standing still either. Andrei was working on preparing the electronics. These are touch sensors. To amplify them, we solder on these copper rings, and we do this 120 times. Meanwhile, a whole week was spent wiring the fiber optics, which were 0.8 mm thick, 0.8 mm. And this took much longer than expected, because every other hole had to be re-drilled. Of course, we checked everything in advance, and after CNC drilling, everything fit perfectly. But there was something we didn't take into account. The fact is, wood is a living material, and such thin holes easily change their diameter, because of air humidity and the application of stain and varnish. As a result, we spent a couple more days re-drilling those holes where the fiber optic cable no longer fit. After the thin background fiber optics have been installed, we move on to the 2 mm thick fiber optics. These points will form the main constellations. As a result, all the future stars are in their places, and from the back side it looks like this. Now we need to lay out the garlands of sensors, untangling hundreds of bundles and threading closed rings through them as we go. Let me tell you, it's not easy at all, but that's not even the main problem. The thing is, all the fiber optics are basically just held in place by a promise in the freshly re-drilled holes. And during the process, dozens, if not hundreds of rods came out of their holes, and we had to track them down and put them back in. Not the most pleasant task, especially after you've been threading them for the past week, and now we have to do it all over again. But to get ahead of myself a bit, I'll say this: even that turned out not to be the main difficulty. So, for the sensors to work as accurately and efficiently as possible, they need to be placed as close as possible to the front edge of the tabletop, but on the underside, of course. These recesses were made for this. We place the ring, press it against the surface, and secure it with glue, so 120 times, losing dozens of fiber optic rods along the way. To stop our table from going bald, I decided to use Head and Shoulders for wood, also known as PVA glue. But even here, to be honest, I messed up and really regretted it later. But I'm telling you everything as it is. I used this method before, when I made a world map with illuminated cities. Here are some shots from that video, and based on that successful experience, I decided to do the same here. To use PVA, but here the conditions are a bit different. Specifically the recesses for the sensors, where the layer of PVA turned out to be indecently thick, and it would have taken a month to dry. Plus PVA is water-based, and the sensors we poured in are electronics, and electronics and water don't mix well. Of course, friends, I looked into this issue, and in theory, after the PVA is completely dry, everything should work. But as you can imagine, it would take a very long time for it to dry completely. So we quickly drain the glue, dry off the residue, and think about how to secure the fiber optics in place. Yes, so that we don't have to wait a couple of weeks. It's not that simple here. For example, here's how superglue and many other compounds interact with fiber optics. Temperature is also important. In this regard, fiber optics is a very fragile and sensitive material. That's exactly why at the time I chose PVA and used it. But to be honest, there are plenty of alternatives. But at the time I just had a very narrow perspective. I've realized that now, after some time looking at the situation from the outside. So we decided to use casting plastic. Overall, it works great with fiber optics. The main thing is not to put it in large volumes, because it heats up a lot. And do you remember what happens to fiber optics when it gets heated? But jumping ahead, I'll say that this was also a mistake. At this point, many of you are probably thinking about epoxy. Yes, as an option we could have used resin, but epoxy takes about a day to cure, and during that time it definitely would have leaked out through thousands of holes. Thick resin comes with its own set of challenges. In such a thick layer, the resin would most likely heat up and could melt the fiber optics. So we ended up pouring plastic over everything. After 15 minutes it dried, and we were very pleased with the result. Still not realizing just how wrong we were. But when it came to securely fixing the fiber optics without any damage, the plastic did an excellent job. So we started assembling the bundles. Here's how we went about it. 20 to 30 rods are placed around the sensor, and a few more are positioned a bit farther away at neighboring spots, and then all of these are bundled together to slightly blur the spot with a gradient. As a result, after a touch, it shouldn't look like a clearly defined round area. A bit later, you'll understand what I mean by this. Each of these bundles is wrapped with tape and labeled. In the end, we need to get 120 properly distributed and slightly interconnected stacks. After a day of work, we have this beauty. Now only a small task remains. Or so we thought. To make it easier to work with the tabletop, we decided to shave it. And then we could freely place it on the table and move on. As you can imagine, by this point the project had already dragged on for a couple of months. Of course, in the meantime we were filming and posting other projects as well. And to be honest, for a long time it was really hard morally to even approach this tabletop. That's why it ended up covered in dust. The next step is to put on a real woodworker's vest and remove the cyber stubble. As you can see, the thin fiber optic cables came out without issues, but the 2mm ones had to be snipped with pliers. After several hours of work, we ended up with a smoothly shaved, but all scratched up, table. To make sure everything would work as intended, we came up with this simple and straightforward assembly kit. This is a small sample piece. An addressable LED strip will be attached to one bar, and on the opposite side a bundle of fiber optic cables will be fixed. Later on, the signal from the touch sensor will be sent to a specific LED that corresponds to a particular area. And within the radius of that area are exactly those fiber optic rods which are gathered into a bundle. Each such pair is placed opposite each other and is enclosed on the sides with an additional partition to prevent light from spilling over into the neighboring fiber optic cable, something like that. As a result, this system proved itself quite well. Later on we refined it a bit, but the principle remained the same. The next step was to start connecting the sensors and linking all the communications together. But what you see on the screen is something completely different. The thing is, after the test launch, the sensors just went haywire. They were triggering randomly, constantly giving off noise. In short, they weren't working as they should. We started looking into the issue and found out that the plastic was amplifying their sensitivity. And as you can see, plastic, there's a lot of it here. Of course, before we started cutting wires, we tried every possible option. But there weren't that many options since we didn't have access to the sensors themselves. And as you remember, we sealed off access with plastic. So the only way to reduce their sensitivity was to change the voltage supplied to the sensors. We tried the entire range, but it didn't produce any noticeable results. We also tried powering them from a battery, but that was just as ineffective. So we decided to install new sensors. In fact, that's what this is for. We are cutting off the old wires. The next step is to properly solder the newly sensor garlands. But even here it's not that simple. We solder, lay them on the floor, connect and test. Everything works perfectly. We lay them out on the table, connect them, and again everything is picking up interference, triggering chaotically. These red LEDs are the indicators for the sensor activation. And as you can see, it's complete chaos. For the next 2 weeks, we tried just about everything. The only thing that was clear was that we needed to reduce the sensitivity of the sensors, but in such a way that they would still penetrate the 1 cm tabletop and work reliably. In the end, we replaced the copper rings with the same ones but made from thinner wire. Made their diameter smaller, experimented with voltage, powered them from a battery, and tried all these manipulations in different sequences. It also became clear that they were interfering with each other. As you can clearly see, the entire garland is triggered quite chaotically, while the button that's a bit farther away works perfectly from a simple touch. But if you glue the ring with a hot glue gun, the sensor starts malfunctioning again, even if you move it away from the garland. In short, it was a kind of absolute hell for 2 full weeks while we thoroughly tested every possible option. In the end, I asked for help with this issue. From Gaver, I think you know who that is. If not, I'll leave a link to his channel in the description. He advised us to install an additional 10 PF capacitor on these buttons. Just so you understand, these are tiny microscopic things. For comparison, we placed a pencil next to them. We had to solder them onto everything. All 120 buttons. Reduced sensitivity of sensors and miraculously started working. Glory to Gaver. And to Leka's patience, at this stage it became clear that the main difficulties had been solved and we could move on to working on the table base. We put off this work until the very last moment because we weren't sure if the idea could even be realized. In theory, a base for the tabletop which would be burning with blue flames might not have been necessary, but it turned out we did need it. Here we decided to go a bit further and make it less primitive than in our previous touch table. To do this, we glued together these blanks, ran them through the jointer and then took them to the planer. After we had 3 perfect beams, we cut them to size and, using the bandsaw, split them in half. As a result, we ended up with these elements. We joined them again, then cut them at an angle. We carefully drilled a crossbar, which is properly called a stretcher, using a crack jig, commonly known as a pocket hole jig. After that, we sand all the parts thoroughly. You often ask what that thing is that collects the dust. It's a filtration system from Powermatic. By the way, this year the company is celebrating its 100th anniversary, and they've set up a cool giveaway where you can win professional machines, and the exact same filtration system. I'll leave a link to the giveaway and the terms in the description. The next step is to fasten together the already glued legs. And as a result we have this kind of table base which still can't hide or fit the fiber optic cable. But that wasn't our goal anyway, since this is just a prototype. During the process we realized how it could be implemented. This idea can be done 10 times easier, and even in such a way that the tabletop will be no more than 5 cm thick, including all the components. But first, we need the prototype, to see the finished result and understand whether it's even worth it. At this point, many of you probably have a legitimate question. Like, I keep talking about prototypes, and that all of this is temporary, and later it will be done properly and look nice. And I do have something to say about that. Our previous touch table project originally looked like this. A lot of people wrote that it was a disaster, not a real job. I completely agree with you, but it was just a prototype. And here you go, here's the improved version of that table. A video about it will be released very soon, version 2.0. Now let's get back to work. To properly illuminate the fiber optics with the corresponding LEDs, we cut out these elements on a laser machine. At the beginning of the video, I showed how it was supposed to work, but in the end we tweaked the design a bit, and now we'll be laying the fiber not in bundles, but in horizontal lines. It's much simpler that way. That's why you can see thin horizontal slits on the template instead of round holes. Once the laser has finished its job, we can start assembling the construction set. We glue the addressable LED strip with the highest possible LED density onto the first slat. This one has 144 LEDs per meter, you can't get any denser than that. We run the fiber optic cable through the opposite slats. On the tabletop, the stars are distributed unevenly, just like in the sky. Accordingly, the number of rods in each bundle is different. That's exactly why we made these slots with extra length, so that any bundle would definitely fit. But the fiber optic cable needs to be fixed more or less evenly. To do this, we insert spacers on both sides and secure everything well with neutral sealant, and of course we smooth it out all around with our fingers. After the sealant has dried, you can safely harvest the excess with wire cutters. Finally, the final assembly. Here, by the way, we decided to do away with the partitions that were present in the first version of the kit. Since the LEDs are positioned very close to the fiber optic strands, the light spillover to neighboring rods that don't correspond to the sensor will be minimal. In fact, this will even work to our advantage, as it will slightly blur the effect with a gradient. I understand that nothing is clear yet, but there is very little left. All that's left is to write everything down correctly so that each button corresponds to the correct P. Couple. For me personally, it's a dark forest. In our team, Lesha is in charge of this, and he coped with this task perfectly. As you remember, in addition to the main background starry sky, we have constellations that we have highlighted in thick. With 2 meter fiber, this made the task much more complicated, because I came up with the idea to make such a mode. Here's the essence of it. The entire tabletop glows with background stars, and if you touch the right spot, the constellation lights up there. It's kind of like a constellation search. I don't know how Lesha programmed it, but in the end, everything worked. Also, let me remind you that these are not randomly scattered dots. It's an accurate map of the constellations. And someone who knows can easily find the intended constellation with a touch. That's exactly why the final bundles of 2 meter fiber optics are assembled using a paper with a star map. As I mentioned, the tabletop was getting pretty scratched up all this time, so it needs to be refreshed. To do this, we lightly sand it. At the same time, we remove hundreds of sharp edges from the cut fiber optics. In the end, the varnish will even out the surface. And jumping ahead a bit, we achieve the effect I had originally envisioned as ideal. The tabletop looks like an ordinary solid piece of wood, and there's not even a hint of the thousands of drilled holes. But when you touch it with your hand, a starry sky lights up in the wood. So let's sum it up. How much effort, time and money did this take? To be honest, I don't know. At a certain point, when it became clear that this definitely wouldn't pay off, I stopped keeping track. We do projects like this solely for content. We don't make any other profit from them. We would love to work on exactly these kinds of complex projects. But obviously, it's extremely expensive. That's exactly why 2 projects to create smart tables are currently on hold. And now, more than ever, we need your support. If this video gets a lot of views, we'll be able to afford such mega projects. Otherwise, we'll have to freeze or abandon them. So it's all in your hands. The best way to help promote the video is to share it anywhere you can. A long comment, a like and a subscription are also very important. A few words about the modes. The first mode is the standard touch mode. The stars light up wherever you move your hand. The second mode is constellation search. The background displays a starry sky, and if you move your hand over the right spot, the constellation lights up. Or several constellations. It all depends on how big your hand is. You can also search for constellations without the background star illumination. And there's another option where the entire starry sky, along with the constellations, shines on its own. Of course, the color of the glow can be anything, since all of this runs on Arduino and addressable RGB strips. Thank you for watching, and may your X stay sharp.